Hello students, today let's start with the derivations of time domain specifications. So we'll start with the rise time. So that is notation is TR. So it is defined as time required for a system or response to rise from 10% to 90% of its final value for overdamped system and 0% to 100% of the final value for underdamped system. So you can observe here the graph here, it's a C of t versus t. So having the 100%, it's a what mark. So this is what the response, which is having the oscillations. Time at which it reaches the 100% of results or input. So that time is called as or defined as rise time. So now we'll consider the derivation, how exactly it goes. For the unit step input, so you can define C of t at t equal to tr, which must be equal to what? 1. This is what at t is equal to tr, right? So we know the time response of an second order system, that is 1 minus e raised to minus zeta omega n tr divided by under root 1 minus zeta square sine omega d tr plus theta is equal to 1, right? So for the simplifying, so we'll get minus e raised to minus zeta omega n tr whole divided by under root 1 minus zeta square sine omega d tr plus theta is equal to 0. So if I equate to this one 0, this term will vanishes. So therefore only term which is left out is sine omega d tr plus theta is equal to 0. So we have the general solution of sine, so which is equal to omega d tr plus theta equal to n phi. Why? Because sine 0, so we can define it as in general solution as n phi. So therefore omega d tr plus theta is equal to n phi. So you can write omega d tr plus theta is equal to pi also, because by considering n is equal to 1. Why? Because it is first time crossing its 100% value, right? So therefore we can write the equation for tr as pi minus theta by omega d, where omega d is the damping frequency, so which is given by omega n under root 1 minus zeta square. So next term we are going to derive now is settling time, that is TS. Time required by an output to settle down within plus or minus 2% of tolerance band, or output becomes 98% and remain plus or minus 2% as tends to infinity, as t tends to infinity. Or else that settling time also can be defined as time required for a system to decrease and stay within the specified percentage of its final value, as given as C of t at t equal to Ts will be 0.98 is equal to 1 minus e raised to minus zeta omega n Ts. So by rearranging the terms, you will get e raised to minus zeta omega n Ts equal to 0.02, taking ln on both sides. So ln with base e raised to minus zeta omega n Ts, which is equal to ln 0.02. So upon simplifying this one, we'll get minus zeta omega n Ts, which is equal to minus 3.912, or else Ts equal to 3.912 whole divided by zeta omega n. So approximately we can write like equation for Ts as Ts equal to 4 by zeta omega n. In general you can write. So more precise, we can use this formula 3.912 by zeta omega n, or else you can generally use this one also, not an issue. Next concept will be steady state analysis. In the time domain specifications, behavior of a second order system. After that, so you need to study how exactly the system behavior in the steady state analysis. This is very important. Steady state is that part of the output which remains altered, transient, completely vanishes from the output. Steady state error means it is a difference between the actual output and the desired output. How exactly the output differs from the actual output. So reference input tells us the level of desired output, and the actual output is fed back through a feedback element to compare it with a reference input. Hence, precision can be what improved. So precise, it can be defined as the difference between input and the feedback signal or actual output. So mathematically, It is defined in the Laplace domain as the Laplace transform of error function, that is E of t, is given as E of s, which is equal to R of s minus C of s H of s. Here R of s is the reference input, C of s is the control output, H of s is the feedback. So this E of s is the error signal. This is for non-unity feedback systems, right? So if I take again Laplace transform of error signal, which is equal to E of s, which is equal to R of s minus C of s. This is for unity feedback systems, means where H of s is equal to what? 1. Now let us look how exactly that derivation of steady state error takes place. Now consider a simple closed loop system using negative feedback as shown in figure, wherein R of s is the input, C of s is the controlled output, H of s is the feedback element, G of s is the forward gain, E of s is the error, B of s is the feedback element signal. That's what we have explained here, all these terms. E of s, B of s, and then E of s can be written as R of s minus B of s, where B of s is what? Product of C of s and H of s. Substitute back here again. So E of s plus E of s, G of s into H of s, which is equal to R of s. We want error signal in this case. We take E of s common here, both sides of this term. So E of s is equal to R of s divided by 1 plus G of s H of s. This is for non-unity feedback systems. If we have a unity feedback system, then this H of s will become what? 1. Therefore, E of s is equal to R of s whole divided by 1 plus G of s for unity feedback system. These two are very, very important. E of t will be equivalent time domain notation of E of s. Now, steady state of a system is at a state at which t tends to infinity. That we need to define now. Therefore, steady state error, which is equal to ESS. This is a new notation. Now, what steady state error means, need to represent it with the term ESS, which is given as limit t tends to infinity with respect to the function E of t. From the final value theorem, we can write limit t tends to infinite at time domain, that is f of t, which is equivalent to limit s tends to 0 s into f of s in the Laplace domain. Therefore, we want error, steady state error. Therefore, limit t tends to infinity, which is for the function E of t, which is equal to limit s tends to 0 s E of s. Therefore, we can write a steady state error, which is equal to limit s tends to 0 s into R of s whole divided by 1 plus G of s H of s. This equation holds good for non-unity feedback system. So if you have unity feedback system, so we can write in the place of H of s as 1. So that's what here steady state error, which is ESS, is equal to limit s tends to 0 s R of s whole divided by 1 plus G of s for unity feedback system. Note here, steady state error depends on R of s and its magnitude, G of s and H of s, open loop transfer function. So this is how the steady state error has been derived. This is the equation. So these two equations are very, very important while solving the numericals. So rest all things we'll discuss in the next class.